Hello, welcome back to the channel. So let's continue our previous video on limiting comparison test and check this integral whether this definite integral converges or diverges by using the concepts of limiting comparison test that we covered in the last video. So if you have not watched my previous video, I'll highly suggest you to first watch my previous video in order to get the full context of what we will be using in order to evaluate whether this definite integral converges or diverges. So again, based on the discussion that we had, for the limiting comparison test, we again choose our second function. And usually, as we discussed in the previous video, the second function is basically the function, the f of x function for large values of x. So what we mean by the f of x function for large values of x is, so let's first write our f of x function. So you know that our f of x function in this case is x plus sine x upon e to the power minus x plus x square. And now we'll have to evaluate what is the behavior of this function. What will this function expression look like when x is very large? So for large values of x, you can clearly notice that e to the power minus x is a decreasing function and x square is an increasing function. So for large values of x, your denominator will become x square, right? Your denominator will approximately be equal to x square because for large values of x, this expression will tend to 0, right? And also, in the numerator, for large values of x, you can clearly notice that the range of sine x is from -1 to 1, right? So it completely doesn't matter how large our x is, sine x will always be in between -1 and 0, right? So we can clearly say that for large values of x, our x plus sine x expression will approximate to x in this case. So now based on this discussion, our g of x function, since our g of x function is the f of x function for large values of x, we can totally assume our g of x function to be simply x upon x square, which would be 1 over x in this case. So that is what we meant by choosing our g of x function, which would approximate our f of x function for large values of x. So whatever behavior you have for your f of x when your x value is very large will be your best guess for your g of x function. So now we have successfully chosen our g of x function. Now it is the time to use limit comparison test in order to evaluate whether this integral converges or diverges. But first of all, we also have to know whether our g of x dx integral diverges or converges, right? And we know that if we are calculating the integral of 1 by x dx from x equals 1 to x equals infinity, which is the same interval, we're basically evaluating the integral of g of x dx, right, with the same endpoints. We know that this integral diverges because if you'll solve this integral, since we have already solved this integral, I'll solve it very quickly. If you'll solve this integral, it will be limit r approaches to infinity, 1 to r, 1 by x dx, and then this will be ln x with the endpoints 1 and r, with the limit r tend to infinity. And then if you'll solve this expression over here, this expression will tend to infinity. So this limit will not exist, which would mean that your g of x dx integral diverges in this case, right? So we know that our g of x dx integral diverges, which is our case 2. We know that our g of x dx integral diverges, and now we have to evaluate the limit of this expression over here. The limit of x approaches infinity for f of x upon g of x in this case. And again, we'll have to check if this limit exists and is also non-zero, which is a very important point. Your limit has to be non-zero. If it's non-zero, then you can clearly state that your f of x dx integral with the same endpoints, which is this original function expression, will also diverge. So now let's calculate, since in this case we have to calculate the limit x approaches to infinity for f of x upon g of x. We know that our f of x is basically this expression. So this would be limit x approaches to infinity x plus sine x upon e to the power minus x plus x square. And now your g of x is 1 by x, right? So if g of x is 1 by x, we can multiply this expression by 1 by x in this case, right? So if we have 1 by x over here, I can take the x in the numerator, right? So our final expression will simply look like limit x approaches to infinity, x square plus x sine x upon e to the power minus x plus x square in this case, right? And now for solving this limit over here, we can take x square common in the numerator and denominator. So this would be x approaches to infinity, x square 1 plus sine x over x upon x square 1 plus e to the power minus x upon x square in this case, right? And now we can cancel these x squares in the numerator and denominator such that your final limit expression will be 1 plus sine x by x upon 1 plus e to the power minus x upon x square. And now you know that for this limit x tends to infinity of this expression, sin x over x for limit x tending to infinity is 0. So this expression approaches 0, which means that the numerator will approach 1. And similarly in the denominator case, if you take limit x approaches infinity, you know that your numerator is decreasing and your denominator is increasing. So again, if you take limit x approaches to infinity for this expression over here, since the denominator is faster increasing than the numerator, so limit x tending to infinity for this expression will also approach 0. So now if you'll solve this expression, your limit expression will simply be equal to 1 over 1, which is 1 in this case. So now your limit for x tending to infinity of f of x upon g of x is equal to 1 in this case. And also you know one more thing about your g of x dx integral, that it diverges. So now based on case 2, we know that our g of x dx integral diverges, and also this limit is equal to 1, which means that it exists, and also 1 is not equal to 0, so our limit is non-zero as well. So since we satisfy all of these conditions for our part B, we can clearly state that this integral over here also diverges. And that is what we proved by only using limiting comparison test in order to prove that the integral diverged. So that's it for this video. Again, feel free to comment down in this video if you have any doubts. Follow the channel in order to get notified about the other videos that I'll be uploading. Stay tuned. Thank you so much for watching. Bye bye. Take care.